When human beings look up at the night sky, the first impression is usually not motion, but stillness. The stars seem to rest exactly where they belong. Constellations recognized by generations long past can still be recognized tonight. A child learns to connect those points of light into shapes, and many years later, those shapes still appear almost unchanged. In ordinary intuition, the sky feels like a surface fixed in place long ago, where the lights above remain nearly the same, while life below is what keeps changing. For most of history, that intuition was so powerful that it became part of the natural way people understood the universe. What changed were the seasons, the weather, and human life itself. But the stars, at least to direct perception, seemed to remain where they had always been. And yet, that feeling does not fully reflect physical reality. In astronomical terms, the night sky is not still. It is always in motion. Most of that motion is simply too slow for a human lifetime, and too small for the naked eye to notice. To realize this, humanity had to replace sensation with measurement, replace visual memory with data, and replace a single night of watching with comparisons stretched across years, decades, and sometimes even longer. Among those countless points of light that seem motionless, there is one star of special interest. It is not brilliant. It is not the first name most people think of when they imagine the sky. It is faint, small, and easy to overlook. Yet, in the language of astronomy, it stands out for a remarkable reason. It has the largest apparent proper motion of any star as seen from Earth. That star is Barnard's star. Why would a star that appears so modest become so important? What is it about this quiet object that has helped us understand interstellar distance, the motion of stars through the Milky Way, the long-lived nature of red dwarfs, and even the possibility of worlds orbiting other suns? To answer those questions, we first have to change the way we look at the sky. Not as a static picture, but as a map drifting very slowly through time. A map whose most important changes do not reveal themselves in a passing glance, but only to those patient enough to measure, record, compare, and wait. And this is where the story truly begins. A story about how human beings learned to measure the shifting of the stars, and how one dim point of light opened a much larger lesson about motion in the universe. Before we continue, Adam Stone would like to quietly thank you for staying here and listening this far. If gentle space and science stories like this bring you a peaceful pause before sleep, please consider subscribing to the channel and leaving a like to show your support. Your support helps Adam Stone continue creating slow, thoughtful stories about the universe, calm enough to stay with you through many nights to come. To understand why Barnard's star is so unusual, we first have to let go of a misunderstanding that has stayed with humanity for a very long time. The calm, stable feeling of the night sky is not proof that the stars are standing still. It only reflects the limits of the observer. The human eye was never designed to store the exact coordinates of each point of light across many years. The brain remembers shapes, it remembers impressions, it remembers the general arrangement. It knows that a constellation still looks familiar, but it cannot easily detect that one tiny point within that pattern has shifted by an almost invisible angle over 10 years, or 20. Measured against the motion of most stars, a human lifetime is simply too short, and that is why the sky so easily creates a persistent illusion. The stars seem to remain where they have always been. To break that illusion, astronomy had to do something very fundamental. It had to separate kinds of motion that ordinary observation tends to blend together. The first kind is the nightly motion of the sky. If you sit outside for a few hours, the stars seem to rise in the east, climb overhead, and set in the west. This is the easiest motion to notice, and it is also the one that once made it natural to imagine the whole sky turning around Earth. But today we understand that this is mostly the result of Earth rotating on its axis. The first thing changing position is not the stars, but the observer. The second kind is seasonal motion. The night sky in January is not the same sky you see in July. Familiar winter constellations withdraw, making room for different patterns in summer. For much of human history, this served as one of the great clocks of nature, tied to planting, harvest, navigation, and calendars. But even this seasonal change is not yet the individual motion of stars. It reflects Earth's changing position along its orbit around the Sun, rather than each star moving across the sky in its own independent way. Only with the third kind of motion do we finally arrive at the stars themselves. This is proper motion, the very slow shift of one star against the background of more distant stars, observed over many years or many decades. This is the key idea behind Barnard's star. When astronomers say that Barnard's star has the fastest motion across the night sky, they do not mean that it is the fastest object in the universe. They do not mean it outruns every other star in absolute speed. More precisely, they mean that, as seen from Earth, its position changes across the celestial sphere with a greater angular rate than any other star identified in classical astrometry. To describe this kind of motion, astronomy needed a geometric model of the sky itself. That model is the celestial sphere, an imaginary sphere surrounding the observer on which all stars are projected as points that can be assigned coordinates. The celestial sphere is not a real physical shell. It is a thinking tool. It allows astronomy to move beyond vague descriptions like near this constellation or above that tree line, and into a language that can be measured, recorded, and compared over time. But even with coordinates in place, one major difficulty remained. The shifts that had to be measured were extremely small. So small, in fact, that they are almost impossible to imagine in ordinary life. That is why astronomy uses very small angular units, especially the arcsecond. 1 degree is divided into 60 arc-minutes, and each arc-minute is divided into 60 arc-seconds. Proper motion is usually measured by how many arc-seconds a star appears to move in 1 year. The existence of such a unit already tells us something important. To study the sky, human beings had to learn how to measure changes far smaller than ordinary intuition can perceive. For a long time, astronomy was mainly the work of cataloguing. Which star is where? How bright it appears? Which group it belongs to? That work was indispensable, but it was still more descriptive than dynamic. Only when measurement became more precise and was repeated over long enough spans of time did star maps begin to reveal that they were not fixed pictures. When observations separated by many years were placed side by side, some stars no longer held the same positions. They were drifting, very slowly but unmistakably. From that moment on, the sky was no longer just a decorative ceiling. It became a space with a history. Each measurement of a star's position did not merely record the present. It created a reference point for the future. The astronomer's task was no longer only to look, but to compare slices of time. There are phenomena that remain completely invisible in a single night, but become clear if one is patient enough to wait for decades. A simple way to picture this is to imagine two moving objects. One is very far away. It may be traveling extremely fast, and yet still appear almost motionless because the angle it sweeps across your view is so small. Another object may be closer. Even if its true speed is less dramatic, it can seem to move much more noticeably. The sky follows the same logic. A bright star is not necessarily the star that reveals motion most clearly. By contrast, a faint star that is nearby and placed in a favorable observing geometry can become a remarkable case in precise measurement. That is why the phrase, "the fastest moving star," has to be understood carefully. It is not the title of a race in the everyday sense. It refers to the way a star's real motion is expressed as angular motion across the sky when viewed from Earth. In the case of Barnard's star, what matters is not its appearance, but the fact that once measurements became precise enough, its motion stood out too clearly to ignore. And the most important thing this leaves us with is not a number, but a change in understanding. We cannot assume that what looks still is truly still. We cannot confuse the nightly turning of the sky with the motion of stars. We cannot confuse seasonal change with the individual journey of each celestial object. Only when those layers are separated does the night sky begin to appear as it really is, a dynamic system, always changing, though most of those changes unfold too slowly for human perception. And once the idea of proper motion becomes clear, the next question follows naturally. It is no longer just a matter of theory, it becomes a question about a person. Who was the first to realize that a faint star was shifting so quickly that it surpassed every case known before it? And how did he do it? From here, the story turns to the man whose name the star now carries. The answer is Edward Emerson Barnard. But what makes that name memorable is not simply the fact that it was given to a star. Barnard matters for a deeper reason. He represents a crucial turning point in astronomy, a transition from observing with the eye alone to observing with images that could be preserved, compared, and measured. Edward Emerson Barnard was born in Nashville in 1857, into circumstances that did not seem to point naturally toward a scientific life. His father died early, his family struggled, and from a young age he had to work in a photography studio to help support them. Yet the place that seemed so far from astronomy gave him two abilities that rarely come together in one person: the sharpness of a patient observer and an intimate familiarity with images as things that could be handled, developed, stored, and compared. For Barnard, light was not only something to see with, it was something that could become evidence. That difference mattered from the beginning. Barnard did not enter astronomy as a conventional product of academic training. He rose through technical labor, through the practical world of cameras, glass plates, chemicals, and photographic processes. Experiences that might have seemed peripheral later became the foundation of his scientific method. He did not look at the sky merely as a spectacle to admire, but as a reality that could be preserved in layers, then compared with itself at another time. Later, encouraged to study more mathematics so he could pursue astronomy more seriously, Barnard bought a small telescope, began to observe systematically, and gradually became known for his comet discoveries. He studied at Vanderbilt, worked at Lick Observatory, and later at Yerkes Observatory. That path makes something very clear. Barnard's talent did not rest only in natural powers of observation, it also lay in his ability to recognize the exact moment when technology was beginning to change astronomy itself. In his era, photographs of the sky were no longer just illustrations. They were becoming a new kind of scientific record. And that is where Barnard's historical importance truly lies. Before astronomical photography became precise enough, an astronomer could describe a star as bright or faint, perhaps note its color, and say roughly where it lay in the sky. But to discover that a faint star had shifted by a very small amount over many years, observing by eye was not enough. Something more reliable than memory was needed. The sky had to be recorded at different moments in time, and above all, it required someone patient enough not to chase what was most spectacular, but to search for what was barely different. Barnard was almost the perfect embodiment of that kind of observer. He did not simply look farther, he looked longer. He understood that some phenomena never reveal themselves in a single night, but become visible only when the sky of the past is preserved and compared with the sky of the present. In that way of thinking, time was no longer an obstacle to astronomy. It became part of the method. The discovery of Barnard's star is the clearest example. From photographs taken years apart, Barnard recognized that a faint star had shifted noticeably against the background stars behind it. In his 1916 publication, he described a small star with a photographic magnitude of about 11 and a proper motion of roughly 10.3 arcseconds per year, moving almost due north. What mattered here was not that he had seen a new object appear. What gave the discovery its importance was that he understood the object had been there all along. What was new was not the star itself, but the knowledge of its motion. That was a profound shift in astronomical understanding. A dim point of light, almost anonymous, suddenly became strong evidence that the stellar background was not fixed at all. It showed that changes of great scientific importance could appear as movements so small that they were almost invisible. Barnard's discovery was striking not because the star was beautiful or brilliant, but because it was too unusual for specialists to ignore. To the general public, a faint star invisible to the naked eye, could hardly become a dramatic character. But to astronomers, that very faintness made the discovery even sharper. It reminded them of something essential. The universe does not necessarily reveal its most valuable truths in its brightest places. Some objects enter the history of science not because they dominate the eye, but because they force measurement itself to change the way we understand reality. For that reason, Barnard should not be remembered merely as an observer with keen eyesight, or as a lucky man who happened to notice something unusual. He belonged to the generation that helped transform the nature of observational astronomy. In him, some qualities of the older era still remained: sharp vision, sustained concentration, long experience at the eyepiece. But in him, the qualities of the new era were just as visible, treating photographs as tools of thought, treating archived data as an extension of scientific memory, and treating small differences between two moments in time as the possible hiding place of a major discovery. Seen that way, the story of Barnard is not only the biography of an astronomer, it is also a lesson in method. Astronomy does not advance only by building larger telescopes. Sometimes it advances through something even harder: the willingness to work with changes that are too small, too slow, and too unglamorous to impress anyone at first glance. And it was precisely through that slowness that photographs of the sky were transformed from keepsakes of observation into instruments for measuring motion in the universe. That is why the fact that the star bears Barnard's name is not merely a surface-level honor. The name is tied to a discovery that turned a dim point of light into a central object in the study of nearby stars. Barnard did not make the star famous in the ordinary sense. He made it readable through measurement. And in science, that is what gives something lasting value. And here the story begins to shift again. We now know who first recognized the star's unusual nature, and how a motion invisible to the naked eye emerged through photography and careful comparison over the years. But that historical discovery opened only the first door. Once Barnard's star stepped out from the background as an object with extraordinary proper motion, a more important question naturally followed. What is it in itself? What kind of star is it? How hot is it? Why is it so faint? And how can something so small endure for such immense lengths of time? The answer begins with the most basic classification. Barnard's star is a red dwarf, a low-mass star of spectral class M. That label may not sound especially dramatic, but it opens into one of astronomy's most revealing paradoxes. The most common type of star in the Milky Way is also one of the least conspicuous in ordinary human experience. If we place Barnard's star beside the Sun, the contrast appears almost immediately. The Sun is a G-type yellow dwarf, hotter, brighter, and far larger. Barnard, by comparison, is much smaller, much cooler, and so faint that anyone who imagines a star only as a powerful source of light could easily underestimate it. Its surface temperature is only a little above 3,100 Kelvin, far below the Sun's roughly 5,800 Kelvin. Its radius is only a small fraction of the Sun's, and its total luminosity is smaller still. That is why, even though it belongs to the group of stars nearest to the solar system, Barnard is not at all a prominent object in the sky to the naked eye. And that is worth pausing over. In ordinary intuition, being close usually means being easy to see. But in astronomy, those two ideas do not have to come together. A star can be relatively near on the interstellar scale and still remain very faint if it simply does not emit much visible light. Barnard is a very clear example of that kind of quiet neighbor, nearby, yet in no way announcing itself through brightness. Its modest appearance is not an exception. It is a trait shared by the entire family of red dwarfs. In fact, these stars make up the largest share of the galaxy. The Sun is often used as the default model in popular imagination, but in terms of sheer numbers, it is not the typical star of the Milky Way. Most stars in our galaxy are red dwarfs, smaller, cooler, dimmer, and much longer lived. In that sense, Barnard matters not because it belongs to a rare category, but because it allows us to study, up close, a nearby representative of the most common kind of star in the galaxy. Even the word red needs to be understood carefully. Barnard is not red in the vivid, glowing sense of a coal in the dark. Its reddish character comes from a lower surface temperature. The cooler a star is, the more its radiation shifts toward longer wavelengths. In Barnard's case, much of its important energy output lies not in the part of the spectrum most visible to the human eye, but more strongly in the infrared. That helps explain how a star can be entirely real, relatively near, and yet still fail to make a strong impression in visual observation. It is not lacking in energy. It is simply radiating in a way that does not favor our senses. But the most important feature of a red dwarf is not its color. It is its longevity. Small stars like Barnard burn their fuel far more slowly than larger stars do. Their low mass makes their light less dramatic, but that same restraint gives them an extraordinary advantage. They endure. While the Sun has a lifetime on the scale of many billions of years, red dwarfs can remain stable for far longer still. Barnard is not a fierce blaze. It is more like a small source of heat, glowing steadily across an immense span of time. The physical reason for that endurance lies in the star's internal structure. In stars like the Sun, the core is where fuel is burned most efficiently, while the outer layers play a lesser role in that process. In red dwarfs, convection can be much more effective, stirring material through the interior and allowing hydrogen to be used more evenly. That means these stars do not consume their fuel in the concentrated, rapid way larger stars do. Barnard shines weakly, yes, but in return it can remain in its stellar state for so long that the whole history of human civilization becomes only a brief moment on its biological clock. And that is why the age of Barnard's star matters so much. It is a very old star, around 10 billion years old, significantly older than the Sun. That age is more than just a number. It tells us that Barnard has persisted through long stretches of the Milky Way's history, and it also helps explain why the star is so valuable to modern astronomy. An old red dwarf often rotates more slowly and shows more stable surface behavior than many younger stars. That makes it especially useful for delicate measurements, particularly the kind used to search for planetary signals. Of course, more stable does not mean completely quiet. Barnard is not a dead object. Though it is older and generally less active than many young red dwarfs, it still shows that stars of this kind can maintain magnetic behavior and flaring at levels serious enough to matter. That point will become especially important later, when the story turns to the planets around it and to the radiation environment within the system. But if we pause here and look only at the basic physical portrait, Barnard appears with remarkable consistency. It is a small, cool, faint star, strong in the infrared, part of the most common stellar class in the galaxy, and capable of an extremely long life because it consumes fuel so slowly. It does not represent the kind of star that usually dominates the public imagination, but it does represent, very well, the kind of star from which the galaxy is overwhelmingly built. And that may be Barnard's greatest value on the physical level. It is not a spectacular exception. It is a nearby object that allows us to study, in depth, a kind of star that is both extremely common and often visually unremarkable. To look at Barnard is not only to look at one individual star, it is to look at a mode of stellar existence that makes up much of the Milky Way itself, slow-living, faintly shining, durable, and extended across spans of time that larger stars cannot easily match. But once the physical portrait of Barnard becomes clear, another question naturally begins to rise. If this star is one of the Sun's nearby neighbors, then just how near is it? And how did human beings measure that distance at all? The question sounds simple, but it leads directly into one of the deepest foundations of astronomy: how we know how far away a star truly is. For objects here on Earth, distance can be measured directly. We can use rulers, radar, or reflected signals. But with a star, all of those familiar methods become useless. No one can reach Barnard's star and measure it by direct contact. Humanity is left with only one path: to infer distance from the geometry of the light the star sends to us. The oldest and still most fundamental tool for doing this is stellar parallax. In its simplest form, parallax is the apparent shift in the position of a nearby object when the observer changes viewpoint. The easiest image is a very ordinary one. Hold a finger in front of your face, then close one eye and then the other. Your finger seems to move against the background. In astronomy, those 2 points of view are no longer your 2 eyes, but 2 positions of Earth in its orbit around the Sun, separated by about 6 months. As Earth changes position, the line of sight to a nearby star shifts slightly against the background of more distant stars. The closer the star, the larger that shift appears. The farther the star, the smaller it becomes. That is why parallax observations are usually compared at times roughly 6 months apart. When Earth reaches the opposite side of its orbit, the viewing angle changes as much as it can, and the parallax effect becomes as clear as the measurement can reasonably hope for. But in practice, it is not as simple as taking 2 snapshots and declaring the problem solved. A star's apparent position is also influenced by its own real motion through space. So astronomers have to observe for longer periods in order to separate 2 overlapping signals. One is the repeating oscillation caused by Earth's motion around the Sun, and the other is the star's true drift through time. And this is where the real difficulty of the method reveals itself. The angles that must be measured are extremely small, so small that the human eye is completely helpless before them. For much of history, even the best astronomical instruments could only just approach the edge of what was measurable. Parallax, then, is not a triumph of visual intuition. It is a triumph of precision. Human beings do not see distance in the ordinary sense. They infer it from tiny positional changes that only very refined measurements can detect. From this method, astronomy developed a special unit for stellar distance, the parsec. In principle, 1 parsec is the distance to a star whose annual parallax is exactly 1 arcsecond. And because 1 parsec is equal to about 3.26 light-years, it becomes a beautiful bridge between geometry and physical intuition. It allows a tiny angular shift on the sky to be translated into a real distance in space. A star with a larger parallax has a smaller distance in parsecs, meaning it is closer. A star with a smaller parallax lies farther away. For Barnard's star, this measurement places it among the Sun's nearest neighbors. Its distance is about 1.83 parsecs, or roughly 5.96 light-years, making it one of the closest stars that human beings can study in detail. But even here, language needs a certain caution. In astronomy, near does not mean near in any everyday human sense. Nearly 6 light-years is still an enormous distance. Light itself, the fastest thing we know, takes almost 6 years to travel from Barnard's star to Earth. In other words, even a neighbor like this remains far beyond direct human reach. And that is precisely why Barnard's distance means more than a number. Once we know how close it is, we do not merely place it on a map of space, we can combine that distance with its apparent brightness to infer its true luminosity. We can combine it with its spectral type to build a more trustworthy physical portrait. And we can use it as a reference point that helps different kinds of measurement support one another. In astronomy, a nearby star is not only easier to observe, it is also an important anchor that makes other facts less uncertain. That role does not stop with Barnard alone. Measuring the distances to nearby stars through parallax forms one of the lower rungs of what astronomers call the cosmic distance ladder. To estimate distances to more remote objects, humanity must rely on more indirect methods. But for those indirect methods to be trusted, the lower levels must first be secure. Parallax is part of that secure foundation. So, every nearby star whose distance is well measured has value not only in itself, but also in helping calibrate the scale by which we measure much farther regions of the universe. With Barnard, that importance becomes especially clear, because this is not merely a nearby star. It is a nearby star distinctive enough that several branches of astronomy meet in it at once. Its measured distance helps make its physical properties more certain. It gives firmer ground to our understanding of its motion, and it turns Barnard into a priority target in the study of nearby stars. It is not simply close. It is close and important enough that its distance becomes central to many larger questions. But Barnard's distance also carries a quiet philosophical weight. It reminds us that most human knowledge of the universe is knowledge from afar. We do not touch this star. We do not travel there. We do not take samples directly from it. Everything we know comes through light, through spectra, through position, and through time. We stand on Earth, reading signals that have crossed the interstellar dark to reach our telescopes, and from those signals, we build the portrait of an object no human being has ever approached. In that sense, parallax is not only a distance measuring technique, it is also a beautiful example of how human intelligence can extend itself through geometry, even when the body cannot go where the mind wishes to reach. And once Barnard's distance has been placed in its proper context, another question becomes sharper. Its nearness helps explain why the star's motion is easier to detect than the motion of much more distant stars. But nearness is still not the whole answer. A nearby star does not automatically become the most striking case of apparent motion. For that to happen, we must also consider its true speed, and the way that speed is projected onto the sky as seen from Earth. And that brings us to the central turning point of the entire story. Why does Barnard's star have the largest proper motion in the night sky? The answer does not lie in just one factor. It comes from the meeting of three things at once. Barnard is relatively close. It is genuinely moving at a substantial speed relative to the Sun, and its direction of motion includes a strong sideways component as seen from Earth. Only when those three conditions come together can a star produce an angular shift large enough to stand out so clearly against the background sky. To understand that mechanism, we first have to separate three ideas that are often confused. Proper motion is the star's angular movement across the celestial sphere. In other words, it is the part of the motion that runs sideways across the observer's line of sight. Radial velocity is different. That is, the part of the motion directed toward Earth or away from it, and it is usually inferred through the Doppler effect in the star's spectrum. And then there is the star's full space velocity, which is its true motion through space once those two components are combined. So what we measure on the sky is only one part of the star's real motion, not the whole story. That is why, when Barnard's star is called the fastest moving star in the night sky, the phrase has to be understood carefully. It does not mean Barnard is the fastest object in the universe. It does not mean it outruns every other star in absolute speed. The statement is true only in a very specific sense. As seen from Earth, it has the largest apparent angular motion across the sky. Its proper motion is a little over 10 arcseconds per year. In astronomy, that is an unusually large value. And yet, it is still far too small for the naked eye to notice over the course of a human lifetime. The first factor is distance. The nearer an object is, the larger the angle it sweeps across the observer's field of view for the same real distance traveled in space. Everyday intuition can help here. An object passing very close in front of you will seem to move faster than one very far away, even if the distant object may actually be traveling at a greater physical speed. The sky works in much the same way. Because Barnard is relatively close, its motion is not compressed into an angle too tiny to notice, as happens with many more distant stars. But closeness alone is not enough. A nearby star could still fail to show an especially large proper motion if its true speed were small. So the second factor is substantial motion relative to the Sun. Barnard is not only nearby, it is also moving quite significantly through the local region of the Milky Way. When proper motion and distance are converted into tangential velocity, even the sideways component of its motion is already large enough to make it stand out. In other words, Barnard does not merely seem to move quickly because it is close. It is also genuinely carrying considerable motion through space. The third factor, and perhaps the easiest to overlook, is direction. A star may move very fast, But if most of its motion lies along the line of sight, almost straight toward us or almost straight away from us, then its sideways motion across the sky can still be quite small. In that case, the observer would not see it sweep clearly across the background, even though its true speed might be large. On the other hand, if a star has a strong component of motion cutting across our line of sight, its proper motion becomes much more obvious. Barnard stands out because it is not only nearby and moving quickly, but also moving in a direction that allows that sideways component to show itself strongly on the sky. A simple image may help. Imagine two airplanes. One is very far away, flying very fast, but almost directly toward the observer. The other is closer, perhaps even somewhat slower in true speed, but crossing sideways through the field of view. To the eye, the second one often seems to move faster across the sky. That does not mean it is faster in an absolute sense. It only means the angle it sweeps across your view is larger. Barnard's star is something like that, on an astronomical scale. What makes it special is not just speed, but angular speed. And this is the point at which the phrase, "the fastest moving star in the night sky," finally falls into place. It is not an exaggerated slogan. It is a precise geometric description. Barnard does not hold that title because it has the most extreme velocity in the universe. It holds that title because, from Earth's point of view, the combination of its distance, its motion, and its direction makes its position change across the celestial background faster than any other known star. Once those three factors are brought together, the picture becomes very clear. If Barnard were only close, but nearly motionless relative to us, it would not be special. If it were moving quickly, but much farther away, its angular motion would be compressed into something much smaller. If it were both close and fast, but moving almost straight along the line of sight, it still would not reveal such a large proper motion. What makes Barnard exceptional is that all three conditions appear together in a single object. And that is also why Barnard occupies such an important place in the history of astronomy. It forced people to understand that a star can be entirely unimpressive in brightness and still become a benchmark in the science of measuring the sky. It teaches a quiet lesson. What stands out most clearly in measurement is not always what shines brightest to the eye. In Barnard's case, the physics of motion and the geometry of observation come together almost perfectly, creating a phenomenon that only reveals itself when human beings learn to read the sky through years and decades of patient data. But once we understand why Barnard seems to move so quickly across the sky, the next question naturally extends beyond the sky itself. That apparent motion is not merely an effect of perspective, it is the visible trace of a real orbit within the gravitational field of the Milky Way. If we look at Barnard only as a star with unusually large proper motion, we are still seeing only the surface of the story. What appears in the night sky is only the projection of a much deeper movement, the motion of a star traveling through the gravitational structure of the galaxy. In other words, Barnard is not simply drifting across our sky, it is following its own path through a vast stellar system, one in which the Sun, too, is moving. This is the first place where ordinary intuition has to be gently corrected. When we say that a star is moving relative to us, it is very easy to treat the Sun as though it were standing still. But the Sun is not standing still. The entire solar system is moving around the center of the Milky Way at tremendous speed, taking hundreds of millions of years to complete a single orbit. So, every measurement of stellar motion is really a measurement made between objects that are all in motion together. We are not standing outside the galaxy watching Barnard pass by. We are observing it from within a moving frame of reference, one that is traveling through the same gravitational structure. Once that becomes clear, the phrase "Barnard moves quickly across the sky" takes on a deeper meaning. It no longer refers only to a rapid change of position on the celestial sphere. It also suggests that Barnard follows a dynamical path that differs from many nearby stars. With modern data, especially from missions like Gaia, astronomers can do far more than measure a star's position and distance. They can reconstruct its three-dimensional motion through space. And from that, astronomy no longer stops at asking where stars are. It begins to ask where they came from, what stellar population they belong to, and what stages of galactic history they have passed through. At that scale, Barnard appears not only as a nearby star, but as a star with a distinct dynamical biography. It does not resemble the younger stars whose motions are relatively calm, and which remain closely tied to the thin disk of the Milky Way, the region where the Sun now resides. Its age, its relatively low activity, its slow rotation, and its chemical makeup all point in the same direction. Barnard is an old star, belonging to an older stellar population, carrying traces of an earlier chapter in the history of the galaxy. And here the idea of the thick disk becomes especially important. The Milky Way is not a single, simple disk of stars. It contains different structural layers. The thin disk is where much of the gas, dust, and younger stellar populations are concentrated. The thick disk contains older populations, formed earlier, with motions that are noticeably different. If Barnard truly belongs to that thicker, older population, then it is not just an old star in terms of age. It is also an object that carries signs of an earlier stage in the building of the Milky Way itself. That is why its motion means more than a number. An old star associated with the thick disk likely formed in a galactic environment different from the one that produced the Sun, less enriched in heavy elements, more dynamically unsettled, and still in the process of assembling its larger structure. Barnard's chemical composition adds another piece to that picture. In astronomy, the word metals refers to all elements heavier than hydrogen and helium. A star with a lower metal content than the Sun usually suggests that it formed from interstellar material that had not yet been enriched as strongly by earlier generations of stars. Barnard is not an extremely ancient fossil of the galactic halo, but neither does it show the usual signature of a young star in the thin disk. It occupies a very valuable middle ground, old enough to preserve the memory of an earlier Milky Way, yet close enough for those memories to be measured with considerable precision. That is why astronomers often speak of something resembling galactic archaeology. They cannot travel back and directly observe the Milky Way as it was billions of years ago, but they can read that past through the traces still preserved in stars that exist today, their orbits, their velocities, their ages, their metallicities, their rotation rates, and their levels of magnetic activity. Each one is like a fragment of a record. Put them together, and astronomers can do more than say where a star is. They can begin to infer which population it belongs to, and which part of the galaxy's long evolution it reflects. In the case of Barnard, this becomes especially clear. The speed we notice on the sky is not just a pleasing effect of geometry and perspective. It is also the observable expression of a deeper reality. Barnard is an old star, following a path unlike that of many younger stars near the Sun, passing through our local region as a surviving witness to an older phase of the Milky Way's life. If the previous section explained why Barnard stands out on the celestial sphere, this one shows that its visibility is really the trace of a deeper, dynamical history. Seen from that angle, measuring Barnard's path is no longer simply a matter of measuring a star. It is more like reading a small line in the motion record of the galaxy that contains us. Barnard is close enough to be measured extremely well, yet different enough from the Sun to remind us that not all nearby stars belong to the same generation of galaxy. Some neighbors are not only nearby in space, they also carry with them older chapters of the Milky Way's past. And here, the story opens into a new direction. If a star like Barnard is small, old, nearby, dynamically unusual, and moving so clearly through our local region, then another question naturally follows. Does it also carry a planetary system? And if it does, in what kind of environment did those planets form, around a star billions of years older than the Sun, and with a somewhat different chemical history from our own? That question leads almost inevitably into another subject, because a nearby star like Barnard is almost certain to become a target in the search for planets. But the reason is not the romantic appeal of a cosmic neighbor. The reason lies in the nature of measurement itself. The closer a star is, the easier it is to separate planetary signals from the background data, and the smaller the star, the more easily the pull of a planet can reveal itself. So, for exoplanet researchers, Barnard has long been a very natural target, nearby, familiar, important, and favorable enough that any signal around it deserves very careful scrutiny. The key method in this part of the story is radial velocity. In principle, a planet does not orbit a perfectly motionless star. The planet and the star both move around a shared center of mass. As a result, the star itself makes a tiny motion, drifting slightly toward the observer and then slightly away again. That motion is far too small to see directly, but it leaves a trace in the spectrum. The star's light is shifted ever so slightly toward red or toward blue through the Doppler effect. From those minute changes, astronomers can infer the planet's orbital period and also a minimum estimate of its mass. So in many cases, the planet is not seen first. It is read indirectly through the way its star is being pulled. But the strength of this method comes with a serious difficulty. The signals are extremely small, and the star itself is not perfectly quiet. In a red dwarf like Barnard, the data can be disturbed by long-term magnetic activity, star spots, rotation, flares, and other internal variations. That is why a repeating signal in the data cannot automatically be called a planet. Before claiming a new world, astronomers have to show that the signal is not being produced by the star itself. And that is what makes the history of planet hunting around Barnard's star such a revealing example of the distance between desire and evidence. For many years, Barnard was seen as an especially tempting target. In 2018, a major observing campaign announced a signal that attracted a great deal of attention, a super-Earth candidate with an orbital period of about 233 days, a minimum mass more than 3 times that of Earth, and an orbit distant enough to inspire many speculations. At the time, the result was seen as a major step forward, but later analyses no longer supported that signal in a convincing way. And that part of the story matters deeply, not because it was disappointing, but because it shows that serious science must never confuse a hint, a candidate, and a confirmed discovery. This is one of the most valuable lessons in the entire story. When a conclusion comes under doubt, it does not mean science has become weaker. Quite the opposite. It means science is protecting itself against haste. The 2018 candidate was not an embarrassing mistake. It was one step in a larger process, a process in which data are tested again under stricter standards, with better instruments, and by independent teams. In exoplanet science, the excitement is always strong. But the data must retain the right to overturn what human beings hoped to believe. The picture began to grow clearer only when more precise observations arrived. Work with espresso in 2024 no longer supported the 233-day planet, but it did reveal a very short signal with a period of just over 3 days and an extremely small radial velocity amplitude. More importantly, 3 other short-period signals also appeared in the data. At that stage, however, not every signal was immediately called a planet. Some were kept at the level of candidates, meaning promising, but still in need of independent confirmation. The turning point came when Maroon X results were released in 2025. With a long and independent series of observations, researchers were able to strengthen confidence in those short-period signals. Once data from multiple instruments were combined, the system looked very different from what had once been imagined. Instead of a distant super-Earth, the clearer picture was a compact system of 4 very small planets, all with masses below Earth's, and all orbiting very close to the star. That changed not only the number of planets, but the way the whole Barnard system had to be imagined. If we look at their orbits, it becomes obvious that this is not a miniature version of the solar system. These planets circle very close to their star, with orbital periods lasting only a few days. The system appears tightly packed, made of small worlds, much closer to their star than the rocky planets of our own solar system are to the Sun. That fact alone tells us something important. If Barnard's star has a planetary system, it is not arranged according to the familiar pattern people often carry in their minds. Even so, the certainty of our knowledge still has to be placed in the right frame. The radial velocity method can only give a minimum mass. It does not directly provide a planet's radius or its true density. We know these worlds exist. We know how they pull on their star. We know the lengths of their orbits. But we still cannot fully describe their surfaces or their internal structures. And because these planets do not appear to transit the star clearly from Earth's line of sight, their true sizes remain an important unknown. In other words, detecting a planet is not the same as fully understanding a planet. There is also another important part of the story. What has not been found? The current data do not support the existence of relatively larger planets in the more temperate region of the system, at least not within the sensitivity limits of present measurements. That leaves the Barnard system looking less like a place where a clear second Earth is waiting to be revealed, and more like a compact, close-in system of very small worlds, with weak signals and a structure quite different from common expectation. And that is why the story of planets around Barnard's star is such a good lesson in how science matures. It begins with expectation. It moves through dispute. It removes conclusions that are not yet solid. And then, slowly, it rebuilds the picture with better evidence. What remains in the end is not a beautiful myth, but a real planetary system. Small, difficult to measure, less flattering to the imagination than many once hoped, yet far more trustworthy. And as the evidence grows stronger, the harder question begins. In an old system, around an old red dwarf, with small planets orbiting so close to the star, is there any real opening for habitable environments? Or does this system mainly help us understand the severe limits faced by worlds around red dwarfs? When the story turns toward the possibility of life around Barnard's star, the right question is not, is someone there? The right question is this: what physical conditions does a star like this create for life? That shift in wording changes the entire standard of judgment. In modern astronomy, a system is not considered promising simply because it inspires imagination. It is considered promising only if it can be analyzed through specific physical factors. The star's radiation spectrum, its age, its magnetic activity, the planet's orbit, the state of its atmosphere, its heat balance, the possibility of liquid water, and the long-term stability of that environment over immense spans of time. Barnard's star is an especially good case for asking this question properly. It is close enough to be studied in detail, yet different enough from the Sun to force us away from the habit of treating the solar system as the default model for habitability. An old red dwarf does not behave in quite the same rhythm as a Sun-like star, and the planets around it do not necessarily follow the familiar climatic path we tend to imagine. The greatest advantage of red dwarfs is time. Stars of this kind consume their fuel slowly, and they live far longer than larger stars. In principle, that is a major advantage for any chemical or biological process that may need billions of years to begin, stabilize, and evolve. If life is not something that appears quickly, then a star with an extremely long lifetime at least provides a wider window in which it might emerge. At the most basic level, this is why red dwarfs cannot be dismissed from the question of life simply because they are small and faint. But an advantage in time does not automatically become an advantage in environment. A star may live for a very long time and still create conditions that are difficult for nearby planetary surfaces. Barnard's star shows this quite clearly. Even though it is very old, it is not completely quiet. High-energy observations suggest that it can still produce flares strong enough to make the radiation environment around it a serious variable. And that weakens a very simple assumption. An old star is not necessarily a gentle star. An ancient red dwarf may be calmer than it was in youth, yet still active enough to place long-term stress on the atmospheres of planets orbiting nearby. And that is where the question of habitability around red dwarfs becomes much more difficult than first intuition suggests. A planet does not only need to sit at a distance where the temperature might, in theory, be suitable, it also has to survive the radiation history of its parent star. If its atmosphere was heavily eroded in the early stages, or continues to be weakened over time by flares and stellar wind, then even a thermally favorable orbit may still fail to produce a stable surface environment. In the Barnard system, as we currently understand it, the picture does not offer a clear candidate for an Earth-like surface biosphere. The known planets orbit very close to the star, which makes them unlikely to be temperate worlds in the familiar sense. But the important point here is not simply to repeat the layout of the system. The deeper point is that, in a system like this, the question of life has to move from a simple form to a more refined one. We can no longer ask only, is there a planet in the habitable zone? We have to ask instead, how does the physical environment of a planet around an old red dwarf actually work? One of the biggest issues is tidal locking. Planets orbiting close to a small star are often likely to end up with one side always facing the star, while the other remains in a long, continuous night. Popular imagination often turns this into an extreme image, one half of the planet burned and blazing, the other half frozen forever. But planetary climate is not that simple. Tidal locking does not automatically mean lifelessness. It simply means the climate problem changes form. If the atmosphere is thick enough, and if convection and heat circulation are efficient enough, then the difference between the day side and the night side can be reduced quite significantly. In some models, even planets that are very unlike Earth can still maintain localized regions where liquid water remains possible. And that leads to another important point. The idea of the habitable zone should not be treated too mechanically. In its classical sense, it means the range of distances where liquid water might exist on the surface of a rocky planet under fairly familiar atmospheric assumptions. But around red dwarfs, the problem becomes far more complicated. A planet close to the star may receive enough energy, yet endure severe radiation stress. A planet farther out may be safer from stellar activity, but receive too little energy, forcing it to rely on a stronger greenhouse effect, or on conditions less Earth-like than we usually imagine, such as oceans beneath ice, or liquid water surviving only in specific regions. So when we say that a red dwarf system does not look like the solar system, that does not mean all biological possibilities are ruled out. It only means the standard of comparison has to change. In this entire problem, the atmosphere may be the hardest and most important variable of all. A favorable orbital distance is not enough by itself. A planet must also retain an atmosphere thick enough to regulate heat, shield radiation, and preserve long-term surface stability. If that atmosphere is stripped away early on, or if it remains too weak to resist stellar wind and continuing flares, then the chances for habitability decline sharply. So, when we evaluate the potential for life around Barnard's star, we cannot look only at the orbit. We have to consider the full history of interaction between star and planet: radiation, magnetic effects, atmospheric dynamics, heat transport, and the ability to maintain a stable surface environment over geological time. That is why the question of life around Barnard's star requires a very disciplined way of thinking. We should not become too optimistic simply because red dwarfs live a long time. And we should not become too pessimistic simply because of flares, tidal locking, or orbital arrangements unlike Earth's. What matters is the synthesis of many layers of evidence: how the star emits energy, how its magnetic activity changes with age, how much radiation the planet receives, how long an atmosphere might survive, and where liquid water could appear, and under what conditions. That kind of integrated approach is much closer to the real spirit of modern astronomy. And for that reason, Barnard's star is a valuable natural laboratory. It does not offer an easy answer, or a comforting one. Instead, it forces us to think more carefully about what habitability actually means. A stellar system does not need to resemble the solar system in order to be scientifically important, and a planet does not need to resemble Earth in every detail in order to raise serious questions about environments for life. Barnard matters because it pulls the discussion away from simple comparison and pushes science toward more complex models of climate, atmosphere, and stellar evolution. But here too we meet the limits of the present. We cannot yet travel to those worlds. We cannot touch their surfaces. We cannot directly sample their atmospheres and test what is happening there. Everything we know still has to come through light, through spectra, through tiny shifts in the star's motion, and through increasingly refined physical models. And precisely because we remain held at that distance, the next question becomes especially important. What technologies are human beings using to continue reading a faint star like Barnard and the planetary system around it from across interstellar space? If, in the early 20th century, the most important discovery about Barnard's star came from comparing photographic plates taken years apart, then in the 21st century, the star is being studied in an entirely different language. It is no longer just a dim point of light whose position changes over time. It has become a layered scientific record. Position, distance, proper motion, spectrum, velocity shifts, brightness changes over time, infrared radiation, and the traces of stellar activity. And that change tells us something profound about modern astronomy. Human beings no longer simply gaze at stars. They extract information from starlight. The first foundational layer of data is astrometry, the science of measuring position. It tells us where a star is, how far away it is, and how it moves across the sky. Missions like Gaia have pushed this work to a level of precision that earlier generations of astronomers could hardly have imagined. For Barnard's star, that precision is especially important because it is one of the stars with the largest parallax and one of the most striking proper motions known. Once astrometry becomes precise enough, the star is no longer just a faint point against a dark background. It becomes an object anchored within the three-dimensional coordinate system of the galaxy, with a position and motion measured tightly enough for other methods to build upon. But astrometry answers only part of the question. It tells us where the star is and how it moves across the celestial sphere. To understand how it is being tugged by planets, astronomy needs another layer of evidence: high-precision spectroscopy. This is where instruments like espresso enter the story. Instead of trying to see a planet directly, these extremely sensitive spectrographs measure tiny shifts in the absorption lines of starlight. Each time a planet pulls the star slightly toward Earth or slightly away from it, the star's spectrum changes by a minute amount. And from those tiny changes, astronomers can infer the presence of invisible worlds orbiting the parent star. What is so remarkable is the sensitivity of these measurements. In systems like Barnard's, the signal astronomers are trying to detect is no longer measured in kilometers per second, but in meters, and sometimes even centimeters per second. In ordinary life, that kind of precision sounds almost absurd, and yet it is precisely at that apparently absurd level that modern astronomy begins to touch very small planets. Instruments like Maroon X push the threshold even lower, turning extremely faint oscillations in starlight into evidence strong enough to support the existence of planets smaller than Earth. With Barnard's star, spectroscopy has another advantage as well. Because it is a red dwarf, its most useful signal is not strongest in the visible range most familiar to the human eye, but farther toward the red and infrared. That helps explain why spectrographs designed for those wavelengths are especially important. They do not merely observe the star with greater sensitivity. They observe it in the part of the spectrum where its physical nature is expressed more clearly. In that sense, modern technology no longer forces the star to speak in the part of light that is easiest for us to see. It learns to listen where the star itself is strongest. The next layer of data is photometry, the measurement of brightness over time. If spectroscopy tells us how the star is wobbling, photometry tells us whether it is brightening, dimming, or being partially blocked by something passing in front of it. Programs like TESS were built precisely for this kind of work. With Barnard's star, changes in brightness over time serve two quite different purposes. First, they can show whether any planets pass across the face of the star. Second, They can reveal internal changes in the star itself, rotation cycles, flares, or longer variations tied to surface activity. This matters because in exoplanet research, the star is not simply a steady background lamp against which planets reveal themselves. Often, the star is the largest source of noise in the data. A cycle in radial velocity might come from a planet, but it might also come from star spots or magnetic activity. A change in brightness might be a transit, but it might also be the star varying on its own. That is why photometry and spectroscopy cannot be treated as separate languages. They have to be read together. A signal becomes trustworthy only if it survives comparison across multiple kinds of evidence. And that is also why observations across many wavelengths matter so much. A star like Barnard cannot be fully understood through visible light alone. Infrared reveals more about the nature of a red dwarf. Ultraviolet and X-rays tell us about its high-energy activity. High-precision optical spectroscopy reveals radial velocity. Time series photometry shows surface variability. Each region of the spectrum offers a different layer of information, and only when those layers are assembled does the star begin to emerge as a complete physical object. This may be one of the most beautiful features of modern astronomy. A star is no longer treated as a single, simple point of light. It becomes a collection of signals that can be separated and read in different ways. From position, we obtain distance and motion. From the spectrum, we infer temperature, chemical composition, radial velocity, and signs of planets. From changing brightness, we learn about stellar activity, rotation cycles, and the chance of detecting a transit. From the infrared, we gain access to stars that are faint in visible light, but rich in information at longer wavelengths. When all of that is brought together, Barnard's star is no longer just a small point near the Sun. It becomes an increasingly detailed record of physical structure, motion, and planetary architecture, refined through each new generation of instruments. That is why Barnard's star is so well suited to long-term research programs. It is nearby, which makes its signals easier to measure than those of more distant stars. Its motion is obvious enough that astrometry becomes especially powerful. And as an old red dwarf, it not only represents the most common stellar class in the galaxy, but also raises difficult questions about stellar activity and planetary environments. More than that, it shows the deeper spirit of observational science. Important discoveries do not always come from dramatic images. More often, they emerge from the stability of measurement, from years of data, from many instruments and many wavelengths, until the noise is worn down and the true signal has nowhere left to hide. And as the technology improves, the question itself begins to change. It is no longer only a matter of whether we can measure Barnard more precisely or detect one more signal around it. A larger question begins to take shape. With a neighbor like this, what will human beings do next? The answer does not lie in thinking that Barnard is a problem already solved. Quite the opposite. The future of Barnard's star is the future of a target that reveals more gaps the more closely it is studied. Everything we know so far, its proper motion, its distance, its red dwarf nature, its compact planetary system, is still only the opening part of the record. Barnard remains a quiet but persistent test of modern astronomical precision. Are there weaker signals still hidden there? Are there longer-period planets that have not yet gathered enough evidence to be confirmed? And how well will our current models of old red dwarfs hold as the measurements continue to tighten? At the first level, the future of Barnard's star is the future of precision. Better measurements do not always produce a dramatic discovery right away. Very often, their greater value lies in making the rest of the picture less uncertain. New data from Gaia will continue to tighten the model of Barnard's position, its parallax, its proper motion, and even the tiniest irregularities in its apparent path across the sky. That alone has real importance. In precision astronomy, a better frame of reference often becomes the condition that allows every other measurement to grow more trustworthy. But astrometry is not the whole story. The other half belongs to ultra-precise spectroscopy. Barnard is exactly the kind of target for which a few more years of data can change the planetary picture in meaningful ways. In a system where the known signals are already very faint, what matters is not a single brilliant night of observation, but the length and stability of the data record. More spectra, more observing nights, and better ways of modeling stellar noise. That is how uncertain signals slowly get sorted into false alarms, candidates, or true planets. So the near future of Barnard does not depend on one explosive moment. It depends on patient accumulation. A little farther ahead, Barnard also stands on the horizon of instruments not yet fully at work, but designed for exactly this kind of problem. Giant telescopes and next-generation spectrographs, including those that will accompany the ELT, are not being built simply to see farther. They are being built to measure smaller variations, more steadily, and over longer spans of time. For a nearby star with a compact planetary system and signals close to the threshold of detection, even a small improvement in uncertainty can open the door to a real difference. Barnard, then, is not just a star that is pleasant to observe. It is a star worth pushing technical limits for. But the future study of Barnard is not only about finding more planets. It is also about understanding the physical environment of the star itself more clearly. The signs of stellar activity already seen in past observations are a reminder that an old red dwarf is not necessarily a completely quiet star. In the years ahead, Barnard will remain an important target for linking many layers of evidence together: stellar spectroscopy, astrometry, high-energy observations, planetary atmosphere models, and exoplanet climate models. In simpler words, it is not only a planetary system to count, it is a laboratory for testing how a parent star shapes the worlds around it. At the second level, Barnard holds a natural place within the map of nearby star astronomy. It is no accident that stars close to the Sun are so often favored in long-term research programs. A shorter distance does not only make signals relatively stronger, it also makes the most basic measurements, from position to velocity, more valuable. Among the stars near the Sun, Barnard has an unusually distinctive profile, close enough to remain a priority, different enough from the Sun to avoid becoming a dull mirror image, and old enough to raise questions that younger systems do not make as visible. For that reason, even if it never becomes the central star of every future mission, it will almost certainly remain in the small group of nearby targets that astronomy cannot afford to ignore. And that leads into the third level, interstellar imagination. But imagination with its feet still planted in physics. Barnard occupies a very unusual place in human thought. It is close enough to appear again and again in serious conversations about interstellar travel, yet still far enough to remind us that the word near in astronomy has nothing to do with nearness in everyday life. At the speeds of our current probes, the journey to Barnard would still take longer than many generations of human lives. That fact forces every realistic discussion of travel there to begin with humility. We do not yet have the technology to turn a neighbor on a star map into a destination within practical reach. And because that distance is so unforgiving, serious interstellar ideas have to move right to the edge of engineering. Concepts such as light sails, tiny probes, or very high-speed robotic designs are not pure fantasy. They are attempts to find a form of technology different enough that the interstellar problem is no longer trapped inside the limits of present-day spacecraft. Projects like Breakthrough Starshot are not promises on the verge of fulfillment, but they matter because they make one thing very clear. If humanity ever hopes to reach nearby stars, it will not be enough to improve existing technology a little. We will have to think in a way that is almost entirely new. Within that logic, Barnard becomes a naturally compelling target. It is not the only possible destination. It is not even the easiest one. But it combines several qualities that keep drawing it back into the technical imagination of our species. It is nearby, it is a single star, it already has a known planetary system, and it holds high scientific value even before any journey is possible. It is no accident that from interstellar probe designs of the last century to more recent concepts, Barnard continues to return as a serious candidate. It is one of those rare names where distance, science, and imagination keep meeting at the same point. And yet, the greatest future value of Barnard may not lie in whether human beings will someday reach it. Its greatest value may lie in the lesson it continues to force science to relearn. The most valuable objects are not always the brightest, the most spectacular, or the easiest for the public to remember. Some stars become important precisely because they allow us to measure the most fundamental things: distance, motion, age, planetary environment, and the limits of measurement itself. And in doing so, they force understanding to change. And here, the film has to return to its final question. After all the measurements, all the data, all the debates about planets, all the models of habitability, and even the very distant dreams of interstellar travel, what is the most important thing Barnard's star leaves behind? How has it changed the way human beings understand the night sky? In the end, what Barnard's star leaves behind is not only the story of a nearby star, it leaves behind a different way of seeing the sky. What human beings once took for stillness turns out to have been, in part, a limit of the senses. The constellations keep their familiar shapes across many generations of life, and yet that familiarity does not mean they are truly at rest. Behind the apparent steadiness of the night sky is a universe in continuous motion, only moving on a rhythm slower than human memory, and subtler than the naked eye can easily detect. Barnard's star is not the brightest star. It is not the most visually striking. It is not the kind of name that settles easily into popular memory. It is small, faint, and almost quiet. And yet from an object like this, astronomy learned how to do things that once seemed almost beyond reach: to measure the distances between stars, to read the true motion of a star through the Milky Way, to recognize the age and nature of an old red dwarf, and to distinguish between a signal that can be trusted and one that still requires caution. And that may be Barnard's most lasting meaning. It forces human beings to separate what we feel from what is actually there. It reminds us that in science, appearance does not determine value. Sometimes a dim point of light can teach more than a brilliant one, provided we measure carefully, compare faithfully, and remain patient long enough for the truth to emerge. In the night sky, Barnard's star does not stand out because of its light. It stands out because it reminds us that some of the greatest motions in the universe reveal themselves only to those patient enough to look beyond the illusion of stillness.